So in the Zoom, we will be 7 participants because, I mean, there is a 5 jury member, the candidate, plus a PhD student of our team that will broadcast the defense on a YouTube channel in live for people at home. Okay. Yeah, I've got the phone number of Bruno. I think I will try to call him. Okay. Okay, so
have you been able to reach Bruno? I've sent him a message as well.
yeah, try to call him, but does not respond. Let's wait a bit. Okay. Hi, Bruno. Can you hear us?
Yes, can you hear me?
Yeah.
Great.
Okay, so everybody's here. So I guess we'll be able to start.
Yeah, so
Okay.
I should start now.
No, I think Renaud is the chairman of the defense.
Okay.
We'll do the introduction.
Okay, so welcome everybody. We are gathered today for the PhD defense of Muxingzi Li. In the committee, we have Hui Huang from Shenzhen University, who also was a reviewer. We have Bruno Vallet from IGN, who was a reviewer as well. We have Nicolas Melado, examiner from IRIT Toulouse. And Florent Lafage, who was the supervisor of this thesis. And as for me, I'm from École des Ponts in Paris. I'm Renaud Marlet. So, Muxingzi, you have 45 minutes to present your work. The floor is yours.
Okay, thank you very much, Renaud. And just before I start my presentation, can I check that if everyone can hear me very well?
Yes.
Okay, great. I'll start now. Okay. Hi, everyone again. Thank you for coming to my defense in the early morning in French time and also in the afternoon of the Chinese time. I'm Mu from the Titan team in Ria Sophia Antipolis. I worked on my thesis under the supervision of Dr. Florent Lafage. Today, it's my pleasure to present you my thesis, Geometric Approximation of Structural Scenes from Images. Compact models are desirable for many applications. For example, it is helpful for modeling large-scale scenes like a city. It enables fast interactive navigation, as rendering compact models is very efficient. It is also helpful for applications based on physical simulation, for example, the energy assessment of a building. To begin with, let's briefly summarize the existing methods for reconstructing compact models. First, compact models can be approximated from 3D data, such as from meshes and point clouds. The first family of work is the simplification methods, which simplify a dense triangle mesh into a coarser mesh by clustering techniques. It can also be applied to point clouds by introducing a graph structure on top of the point clouds. Another class of work analyzes the connectivity relations between planar primitives extracted from a point cloud, and they reconstruct the final model by closing the gaps. Space partitioning is another technique, which consists of first partitioning the 3D space into a collection of polyhedron cells, and is followed by selecting faces that enclose the underlying shape. The surface is extracted by assigning inside or outside labels to the cells. This step is a discrete optimization problem with a relatively high algorithmic complexity. Many works have also explored reconstructing compact models from images. As pure image-based approaches are more challenging, the majority of these work focus on specific applications. For instance, several approaches have been proposed for building reconstruction, either by estimating height for extracted building footprint, or by modeling the roof structure as a graph. The second family of methods work on estimating the layout of a single room from one panorama image. Recent approaches train neural networks for the prediction of corners, layout surfaces, and boundary maps such as floor wall and ceiling wall boundaries. The house scale estimation can be achieved by taking multiple input images, but this requires some advanced technique for combining the output estimation of each of the input. Several methods also consider floor plan vectorization. The vectorized floor plan is a good representation of the layout. This line of work focuses on recognizing floor plan elements such as junctions, doors, windows, and different types of rooms. These methods are constrained to certain types of structures and are dependent on the diversity of the training set. Polygonal image segmentation methods represent objects of interest with floating polygons. This representation is more generic and can be applied to urban scenes when properly adapted. This thesis explores the problem of low-cost image-based compact model reconstruction with a focus on urban objects. The input consists of one overhead image, for instance, a floor plan image, and a sequence of multi-view stereo images, such as images of the building's interior. The overhead image could also be an orthophoto from aerial shots, and the image sequence could be images of the building's exterior. The output will be a 2.5D model that is aligned with the multi-view stereo images. The algorithms are designed with several objectives. First is fidelity, meaning that the output should conform to the observed data. The second objective is simplicity, that is, the output should keep low complexity. Automation is a necessary condition for many practical applications with large amount of data involved. Last, although the overall pipeline will focus on urban objects, applicability means that the individual components that we design for the pipeline should be applicable to diverse types of objects and scenes if possible. Overall, reconstructing compact models of structured scenes from low-cost image data is a challenging task. It poses several scientific challenges. The first is to deal with defects in the low-cost data. Images captured from real world are often corrupted with noise and blur. The lighting condition is another factor that can significantly affect the image quality, as shadows and overexposure may result in loss of information and hinder the process of affected regions. Presence of unwanted objects is also frequent when reconstructing urban structures. For example, vegetation and other background objects can sometimes be captured, leading to a corrupted multi-view stereo point cloud. The second challenge is to deal with data collected from different sources. On one hand, the floor plan images are not drawn according to the same style and might not be as clean as scanned image. On the other hand, the pipeline needs to relate the 2.5D model created from the floor plan to the multi-view stereo data. The level of automation is another challenge. While the interactive techniques are known for achieving high accuracy, practical applications at a large scale requires a high level of automation. We need to consider a good balance between the amount of user intervention required and the degree to which the level of accuracy can be relaxed. The last challenge is scalability. The level of complexity and styles of things may vary greatly from one to another. Some existing methods rely on strong geometric assumptions on the regularity of objects, such as the Manhattan word assumption, which assumes all surfaces are aligned with 3 orthogonal axes. These techniques have difficulty when generalizing to other things. On the contrary, assumption-free approaches are more flexible, but their results tend to be less structured. Ideally, a good method should explore more general characteristics of objects and be able to generalize to a diverse set of things. From the input described previously, I propose a pipeline for generating a compact model focusing on the interior of the building. On the top, the input floor plan image is first converted to a vectorized form. The 2.5D model can be generated by extruding the floor with an estimated height. On the bottom part, the point cloud is first obtained from input image sequence using state-of-the-art structure from motion and multi-view stereo reconstruction algorithms. Finally, the model is registered to the point cloud to output an aligned model. Optionally, the texture can be added to the model by projecting colors from the registered raster images or from the color of the point cloud directly. There are two main contributions of my thesis. The first is a polygonal image segmentation method that is capable of vectorizing a floor plan image. The second is a multimodal registration method that registers a polygonal mesh and the point clouds of different scales. The rest of my presentation consists of three parts. First, I will introduce the algorithm for polygonal image segmentation. In the second part, I'll present another algorithm for the task of 3D registration of multimodal geometry. The last part demonstrates a potential application of the two previous algorithms by combining them into the pipeline for generating a compact floor model. Now, I will introduce my algorithm for the task of polygonal image segmentation. This algorithm is designed to be generic and can be applied to converting a raster floor plan image into a vectorized form. Various ways exist for representing object silhouettes. Low-budget bounding boxes are the most compact representation, but they ignore shape details. Chains of pixels describe well the individual shapes, but ambiguity might exist around fuzzy boundaries. In this work, we focus on representing object silhouettes with polygons as a good compromise between the two. First, let's review some prior work on object polygonalization. A popular strategy consists in extracting first the pixel chains from semantic segmentation and simplifying them into polygons. Their output can easily drift from the object silhouettes. There are also neural network approaches. Polygon RNN and Polygon RNN++ sequentially predict the vertices, and curved GCN reallocates a fixed number of initial control points simultaneously. These works lack the geometric guarantees. For instance, they do not prevent overlapping nor self-intersection. Cell grouping methods oversegment an image into polygonal cells. The cells are grouped into different classes using algorithms such as GraphCut or MCMC. The output relies on the quality of the initial partition, which can sometimes be imprecise. The key idea of my work lies in refining the geometry of an imprecise polygonal partition. The goal is to design an efficient exploration mechanism that searches over a very large space of possible configurations and to produce an output with geometric guarantees. The proposed algorithm takes as input an image with its rough semantic probabilities. Starting from an inaccurate partition, we propose a refinement step which consists of locally splitting and merging cells, guided by an energy that defines on both the image and the partition. The output are low complexity polygons capturing the objects. By construction, the output polygons are guaranteed to recover the entire image domain without intersection and not contain adjacent cells with the same semantic label. I propose an energy function for measuring the quality of semantic polygonal partitions. The fidelity term penalizes when the face label do not conform to the probability map. The complexity term encourages the low complexity polygons with fewer edges. Oh, there is another fidelity term that also penalizes edges that do not align well with the image gradients. Okay. Now let's look into the fidelity term. The first term is a semantic loss, and the second term is a gradient alignment loss. Both of them are normalized according to the image size. The gradient alignment loss aggregates per pixel deviation along each edge. The direction of pixel gradients is modeled as a Gaussian distribution around the edge's normal. The two terms are balanced by a parameter lambda between 0 and 1. As shown in the crops, increasing lambda would lead to more compact yet less accurate polygons. Overall, we need to solve a discrete optimization problem inspired by geometry processing algorithms. We explore the large solution space via an iterative mechanism based on two local operators that split and merge faces of the partition. The merge operator simply merges two edge adjacent faces by removing their common edges. The split operator first detects a set of line segments, which are then prolonged to segment the face into subfaces. Adjacent subfaces with the same semantic label are immediately merged. The exploration mechanism iteratively updates the polygonal partition using merge and splitting operators, maintained by a priority queue. The priority queue assigns highest priority to the operation which decreases the energy the most. Thanks to the guidance of the global energy, the exploration mechanism avoids path-dependent routes and has a natural stopping criteria. To sum up, the algorithm departs first from an initial semantic partition associated with a priority queue as described before. The exploration mechanism iteratively refines the partition in a greedy manner. The algorithm stops when there is no more operation that can lower the energy. On the right is a visualization of the exploration mechanism. We can see that some regions, like the dog's nose, that are originally inaccurate, they are corrected by splitting and merging process. As compared to non-local methods like simulated annealing, starting from the same initial partition, the greedy optimization scheme achieves similar optimum while being orders of magnitude faster. This example shows the impact of different initialization methods on our results. Objects of interest here are person and bike. In the first column, we start the exploration mechanism from a partition composed of one rectangular facet. The result misses the bike object. This is because the greedy optimization sometimes gets stuck in a local minimum. Using an over-segmentation as an initial partition helps our algorithm to converge to a better configuration, as shown in the second and the third column. Our algorithm performs the best from the connected partition as an initialization, which gives a good trade-off between accuracy and complexity. This option returns similar results as the simulated annealing in the last column, but it costs much less processing time. We compare the algorithm to two families of existing methods. The first are the vectorization pipeline, including Douglas-Pecker and the polyline simplification. The second are cell grouping algorithms, including Voronoi partition and KIPI. The same probability maps are provided as input to all methods. The experiment is conducted on the HKU-IS dataset and the Pascal VOC 2012 dataset. While the accuracy of most methods drops quickly at high compression rates, our algorithm retains a high accuracy. Here are some results on the Pascal VOC dataset. The probability maps produced by DeepLab v3 are shown alongside each example. These probability maps are sometimes ambiguous. Our algorithm can capture well the silhouettes of these objects with low complexity polygons. On the bottom right, it shows a failure case. Here, the quality of the probability map is too poor to capture the underlying objects. For example, the lady's head. Here's a visual comparison at low and high compression rates. Unlike other methods whose output can easily drift from the object silhouettes, our approach can follow well the object contours despite a decrease in the complexity of the output polygon. The algorithm is further validated on the building extraction task. When used in conjunction with UNet, it obtains the best average precision and average recall. Effectively, this means that a two-step pipeline with our method as a post-processing polygonalization step can be able to outperform task-specific neural networks such as Polymapper. This visual example shows that despite the compact representation, the proposed algorithm can capture some fine details of the building. The potential of this method is further demonstrated on floor plans, the lines, and as well as the line sketch drawings. It is capable of vectorizing linear structures in such type of scenes. To conclude this part, I introduced an object vectorization algorithm which outputs low complexity polygons with a geometric guarantee of being intersection-free and forming an image partition, as well as a semantic guarantee to have no adjacent cells with the same semantic label. Finally, the local optimization scheme offers fast convergence in practice. Now, let's proceed to the registration of multimodal geometry. The algorithm takes as input a surface mesh and a point cloud. The relative scale between them is unknown. The output is a similarity transformation that aligns the pair. In real-world applications, we sometimes encounter different types of geometric data describing the same underlying scene. Physical measurements often record the acquisition in the form of point clouds and dense meshes. Also, there may exist compact model created by CAD artists or by automatic approaches such as procedural modeling. Different sources of data are usually saved in different coordinate systems, and they are required to be registered to the same coordinates before passing to applications that depend on both of them. We review some prior work on multimodal registration. One of the most straightforward approaches is to extend ICP by integrating a scale update step inside each iteration, which has been explored in both traditional methods and learning-based methods. Probabilistic approaches represent the point cloud using a Gaussian mixture model and cast the registration problem as a maximum likelihood estimation. These methods can estimate a combination of similarity transformation and non-rigid transformation. However, they can be trapped in local minima. There are also a number of two-stage methods consisting of a scale estimation step followed by a registration step. One work utilizes a logarithmic scale space in which shape scaling corresponds to a shift in the profile. Another work uses the oriented bounding box for estimating the scale of each object of interest. The key idea of my approach lies in a planar shape-based representation for the underlying object. It comes with three advantages. The first is that the planar shape detection methods offer good robustness to noise and outliers in comparison with directly working with raw point clouds, as we can see from the example on the right. Second, it gives a natural approximation of the distance field of the underlying surface. Third, it adapts well to man-made structures. Starting from the input composed of a point cloud and a surface mesh, The proposed algorithm first extracts a set of planar shapes from the pair using region growing. For each set of the planar shapes, we analyze their surface model distribution, as illustrated by the arrows. We estimate 3 dominant axes from the distribution using the EM algorithm. These axes are not necessarily orthogonal to each other. The pair of 3 frames are aligned, leading to a total of 24 possible rotations. The refinement step takes each candidate rotation and estimate a final similarity transformation. The result with a minimal loss is kept as a final output, as indicated by the red frame. First, I will explain the alignment of the 3 frames. A 3 frame can be written in the form of a 6-column matrix. Every 2 columns represent 1 dominant axis, including both positive and negative directions. We exhaust all 6 permutations of the 3 axes, as well as all combinations of the orientation of each axis with the right-hand rule applied. This gives us 2 to the power of 3 divided by 2 orientations for each permutation. Therefore, we have 24 candidate rotations in total. Here are all the candidate alignments after applying each rotation. The best candidate is highlighted. As a follow-up step is a local refinement step. The remaining 23 candidate alignments are unlikely to output good final results. For the refinement step, I propose an energy that allows continuous optimization of parameters of a similarity transformation. The energy takes a symmetric form that removes undesirable global minima due to scale variations. The distance fields here are normalized beforehand in order to balance the losses contributed by the 2 terms. With the help of Li algebra, we can use the gradient-based optimization to solve for the 7 parameters representing the similarity transformation. The derivative of the energy function is shown here. The optimization is finally solved by the trust region method. This example shows the results of applying refinement to all candidates' alignments. The root mean square error is listed to indicate the improvement brought by the refinement step. The best result is highlighted with a red frame. The experiment is conducted on a collection of 19 objects, including both real-world multi-view stereo point clouds and synthetic data. The dataset is divided into 2 categories, free-form objects and regular objects. We consider an object to be regular if it has a high degree of organization in the form of large planar structures, for example, the buildings and the furniture. To demonstrate robustness of the proposed algorithm to noise, we add Gaussian noise to the example point cloud. Comparing the 3 frames of the point clouds with and without adding noise, we can see that the estimation of 3 frames is robust to noise. Therefore, the algorithm is able to generate good initial rotations for noisy input. It could also work on free-form objects like the additional example, even though the 3 frame for the point cloud of the horse is impacted by the noise. The algorithm is compared with 2 families of baselines. The first are 2-step methods, which consist of a scale estimation step and a registration step for recovering rotation and translation. We supplement the state-of-the-art registration methods with a bounding box-based scale estimation step to make the 2-step methods. The average and the maximal root mean square error are reported metrics to indicate the average alignment quality and the failure rate. Traditional feature-based global approach like FGR and probabilistic local approach like filter reg do not perform very well on this dataset. DCP is a point-based learning method. It fails because of its limited capacity on the number of points that it can possibly process. In contrast, the volumetric-based learning methods, DGR, achieves better results among them. The second family are joint methods, which estimate the similarity transformation in a unified fashion. The proposed algorithm performs best on regular objects, as they are well described by piecewise planar geometry, as shown on the right. It reaches lower average and maximal root mean square error for more than half of the objects. The failure case, building A, is due to its very noisy normal of the input points. For freeform objects, as indicated by the left part, the proposed algorithm matches the accuracy of the state of the art. Here is a qualitative comparison on a freeform object and a regular object. The input point clouds are significantly perturbed from the ground truth alignment. For local methods, we show their results with and without Rorschach initialization. Classical methods like ICP and FGR do not offer enough robustness to variations in the shape characteristics. Probabilistic approach like FilterRec benefits more from Rorschach initialization as compared to the ICP family. DCP fails to register point clouds with large numbers of points due to its high memory consumption of the transformer architecture. DGR is able to produce more accurate correspondences. Our method recovers well the alignment for both types of objects, achieving a good level of accuracy. Here's a comparison of each method on the recall rate on the different threshold. The proposed algorithm matches the accuracy achieved by the state-of-the-art baselines on freeform objects while outperforming all baselines on regular objects. I also investigated robustness to different types of transformation perturbations, including rotation, translation, and the scaling. As we can see from the plots, the proposed algorithm achieves competitive stability to all three types of perturbations. To conclude this part, this is a global registration algorithm for multimodal geometric data. It is designed to incorporate relative scale estimation in a joint optimization framework. It offers robustness to noise and outliers in the input point clouds. It is applicable to both regular and the freeform objects. At this stage, I will demonstrate a potential application of the two algorithms by integrating them into the proposed vectorization then registration pipeline for floor modeling. To recap, the floor plan image is first converted into a vectorized form. The interior region is indicated in gray. The vectorized floor plan is extruded to create a 2.5D model. A point cloud is reconstructed from the input image sequence by state-of-the-art methods. In the end, the model is registered to the point clouds to output an aligned model. In order to apply the polygonal image segmentation algorithm to the floor plan images, we need to supplement it with a method that estimates probability maps from different types of floor plan images. Here, I use a naive approach based on clustering of pixel colors. The pixels are first clustered to a fixed number of clusters, and then further grouped into two classes with the help of user input. Here are the results on some floor plan images. Note that the algorithm can capture well the thin walls. Some more results are shown on grayscale floor plans. In this case, the probability map is simply taken as the image itself, normalized to the range of 0 to 1. Dilation and erosion are applied to remove very thin lines corresponding to stairs, doors, windows, and some furniture. This gives us a cleaner probability map with our naive approach. The next step is to extrude the interior part of the factorized floor plan into a 2.5D model, according to an estimated height. The interior part is obtained by inserting the polygons into a constrained Delaunay triangulation and marking the triangle faces of the interior region. The extrusion height is estimated by computing the ratio between the height of the point cloud's optimal bounding box and the length of the diagonal of its base face. Here I show some results for building interiors. The last two columns visualize the aligned floor model using a simple coloring strategy. The color at each point on the mesh surface is simply taken from the nearest point of the point cloud. More advanced texturing techniques can be used for producing a better texture map. The pipeline is also applicable to building exteriors. In this case, the point cloud of the output scene may contain structures that are absent from the floor plan. For instance, the roof structure cannot be inferred from the floor plan. We test the impact of defects in the input point cloud by simulating random noise and incomplete acquisition. The registration step, as we can see, is more robust to random noise on the point locations, but it tends to fail in case of low overlap between the input pair. On the contrary, the simple coloring strategy is more sensitive to noisy point clouds, resulting in undesirable artifacts in the texture. The proposed pipeline has a few limitations. The naive approach for estimating the probability maps for floor plans requires some user input and is limited to floor plans with strong color cues. More sophisticated semantic-aware methods can be used for producing probability maps from more complex floor plan images. The quality of the reconstructed floor model is affected by the presence of structure with heterogeneous heights. The current pipeline, however, considers only a uniform extrusion height. The absence of building structures, such as roof, door, and windows, result in discrepancy between the extruded model and the point cloud. This indicates that we need to add to the pipeline additional steps for reconstructing the missing structures. Now, I will finish my presentation with some conclusion. I investigated the problem of geometric approximation of urban objects from images in the form of compact and accurate meshes. I proposed two generic algorithms. One is for the refinement of polygonal partitions of 2D images with geometric guarantees. I designed an energy for measuring the quality of each partition configuration and introduced an efficient exploration mechanism. The other is a 3D registration method for multimodal geometric data of different scales. I proposed a planar shape-based representation that is robust to noise, and it adapts well to memory structures. Also, I formulated a continuous optimization problem for joint refinement of rotation, translation, and scaling. The applicative potential of these algorithms is demonstrated by a pipeline for floor modeling. Finally, I'll discuss some perspectives that could be explored for future research. First of all, the proposed algorithms focus on linear geometric primitives. Therefore, a natural extension of this work would be to support more complex objects, including curved shapes using Bezier curves, or NURBS. These techniques would allow us to capture freeform objects with a better trade-off between complexity and distortion. Secondly, my pipeline is proposed under the assumption that the object of interest is well captured by the input data. In particular, the registration algorithm assumes a sufficient amount of overlap between the input pair of geometry. Adapting to partial alignment would open up new application fields for the pipeline. Moreover, our representation can be enriched by introducing semantic labels to the data. For instance, one possible direction would be to design advanced methods for classifying pixels in floor plans to generate semantic probability maps and takes into account components other than just the walls. Another way would be to integrate a semantic component for separating objects from the building's interior. This would allow us to generate a cleaner floor model. Finally, the ultimate goal is to have an algorithm that automatically reconstructs a whole building, including the exterior structures, interior layout, and even furniture inside. This requires the integration of specialized pipelines for both outdoor and indoor scenes into a single unified framework. I hope that my research could help us get a small step closer towards this ultimate goal. Thank you for your attention, and thanks again for coming to my defense.
Thank you very much for your presentation. We now are going to ask some questions regarding your work. Maybe we can start with Hui Huang, who was a reviewer of your thesis.
Okay. So yeah, I totally agree that reconstructing a compact model has a very important practical value for these digital applications. So your thesis proposes a building modeling method that uses a polygon image segmentation method for the 2.5 model generation and a 3D registration method for the registration of the generated model under the point cloud. So I think the whole thesis I reviewed. So the whole thesis exposition is very clear, and the evaluation experiments are sufficient. Also, the results clearly demonstrate that your proposed method achieves state-of-the-art performance. However, I do have I think several minor questions. So it seems that the optimization of the polygon image segmentation you proposed in chapter 3 is greedy, right? So would this method always achieve like a global optimum?
For the image for the polygonal image segmentation method, yes, as you said, it's a greedy optimization scheme. So it relies on the initialization to be somewhere close to what we want, and this happened to be achieved by over segmentation methods. So there are many like polygonal image segmentation methods that already over segment the image, and this could help the greedy method to get to a global minimum. But if we start from a very simple initial partition, like just a rectangle, as I showed in one of the slides, it takes some time to put up the slide. But as shown in one of the slides, I showed that if we start from just a rectangle, it can sometimes get stuck in a local minimum and no longer process the partition. And in that case, we also tried to use simulated annealing method to check if the operators can continue to work if stochastic optimization is allowed. Well, it works, but costs too much processing time. That's why in the end, we opt to use an over segmentation as an initial partition and the greedy method for fast convergence.
Okay. Okay, I think you answered the question very well. So then move to the chapter 4. So the registration algorithm you proposed in chapter 4 actually, I think you also pointed out during your presentation, it actually depends on this accurate the calculation of this normal distribution, right? And if we have this real scan data incomplete, so this assumption is easily can be violated. And also for extreme case of this smooth manifold like this free form distribution, also I think there. So have you? Maybe I missed, but have you tested on this like kind of like this stress test to check how far this registration algorithm can go?
For the, in fact, I have not tested in like on a very large range of freeform objects for the because time is limited. Okay, but the methods is well, as you say, it's reliant on how reliable the three frames that we can estimate from the distribution of the normal. So for some freeform objects, like if we have very smooth surface and the distribution is more or less uniform in the 3D space, like if we have a sphere, and then it would actually work because we use EM algorithm to find the three clusters of the normal direction in the spherical coordinates. And in this case, the EM algorithm would give us just something like the XYZ axis, and for both the input point clouds and also the surface mesh. So in that case, it would work. However, for freeform objects that does not clearly have three main directions, and maybe it has like 6 main directions, and then each time our EM algorithm converge to like 3 of them for this example, and another 3 main directions for the mesh input. Then in that case, it could be difficult to get to a global minimum.
Okay. So another is just due to my curiosity. So actually in your last slides, like you were talking about is perspectives, right? So I think the last one you say is how to like combine this the exterior and the interior contraction. I think that is a very promising and interesting kind of direction. It's actually also we are thinking about it. So have you like any like more thoughts, or have you kind of like a try on along this direction?
For now, I have not tried exactly on this direction, but according to the reading I have done and some thoughts that maybe we can like we should maybe discuss it in several cases, like for example, like a house. If we have the floor plan of the house, this floor plan, we can extract the interior layout from the floor plan as well. In fact, for the house, the floor plan already also give us some intuition about how the exterior would look like. So in that case, this floor plan can actually use for both interior and exterior reconstruction, and they are on the same coordinates already. So once we can map the interior to the inside of the floor plan and exterior to the outside of the floor plan. That gives us like a one building, like one house model. But for some buildings that are way more complex, like buildings of like a lot of which doesn't have a single floor plan, or it has a very strange structures, then currently I have no thought of how to make the 2.5D model to fit those buildings.
Okay, thank you. I think I have done a round of these questions. Yeah.
Okay. So maybe we can move to the other reviewer, who is Bruno Vallet. Bruno, do you have some questions for you?
Yeah, thank you. Well, I will start with some comments. So first, I wanted to thank me for a very nice presentation. It's very clearly presented. I won't have that many questions because I know her work already pretty well. I was in her thesis committee. I'm also coordinating the Biome project that this thesis is part of. So about the Biome project, I was interested to see that she was supposed to work more on the inside of the building, but in fact, the methods that she developed could also be useful for the outside shell of the building. So that's a very interesting contribution of her work. And finally, I'm also part of now a new project called AI4Geo, where we are benchmarking methods for building outline extraction. And we are benchmarking AZIP, and I wanted to thank Mu because we interacted with her a lot to solve a few problems we had with our code. And now everything works very well. We've been able to run it on thousands of buildings over the city of Toulouse. And we had the first results yesterday, and it seems that for the moment, AZIP is the one that performs best on most of the metrics. So I wanted to congratulate me because yeah, the algorithm is really efficient. I also wanted to thank me because it's good to see that you can still do significant work in computer vision without deep learning, with good geometry and good optimization, and that's something I particularly enjoy. So now for the questions. So first, I wanted to know, because you used in two very different contexts, your AZIP method on ortho images and on floor plans. And my question was, how complicated is it to tune between these two very different contexts?
Oh, so for the method to adapt to the different types of objects, as we can see from the energy function that I introduced before, it has like a parameter lambda that we have to tune based on how complex the thing is. Because I will go to the slides for the energy. So for the energy term, the first term we have already normalized it according to the image size, but the second term we left it to the choice of the user, and it's purely on the number of edges that we want to discourage. So if we put the lambda very high and on a very complex thing like an aerial image of the city's neighborhood with like hundreds of small buildings inside, then putting this lambda too high would just make the buildings disappear because the energy is just too high for some small pixels. So in that case, we have to decrease this lambda to adapt better to this thing of like a lot of small objects. If we have a thing that is if we have orthophoto just of a building, we have the exact crop already, then we can put the lambda higher. It doesn't matter because it already occupies a large amount in the crop, and it can give us the more regular shape of the building. So it's kind of dependent on how complex the final output should be.
Okay, thank you. For me, our method is kind of bottom-up, and usually bottom-up methods are quite sensitive to under detection. So for instance, in your input polygonal partition, you are missing a building edge because it was partially hidden by a tree or because it wasn't a very sharp edge. How is potentially is the building going to be very, very wrong? Or you have something that allows to get more robustness in these cases?
In this case, like if the building is blocked by, like if a corner of the building is blocked by a tree, but if the edge of the building are like sharp enough for us to detect the line segments, and in that case, since on the tree it's less likely that we can detect the line segments as the image gradient is more or less randomly distributed. In that case, the algorithm might be able to prolong the building's edge from the two adjacent sides to enclose the whole building. But it depends on how the probability map would actually tell us. So if the probability map of the building is relatively weak, then in that case, the algorithm might not think worthy to prolong the edge and include this corner. And so it's a work. So it's a work that depends on both our method and the input semantic segmentation that we can have.
So for me, our method is trying to solve two different problems at once. One is the problem of binarization, let's say image-aligned binarization of semantic segmentation. There are some works like GrabCut that tries to make a binary segmentation of semantic segmentation that is as aligned as possible with image gradients and the vectorization part. And so how do you think your method compares to, is it better to solve both problems at the same time or to split them into separate problems?
Well, so for tackling this problem in a two-step way, like first binarization and then with the polygonalization step, it can sometimes induce some problems. For example, if we have two objects that have just adjacent to each other, and from the binarization we can extract we can maybe extract one object, and then we do binarization on the other object. We have two objects, and then in that case, if we do the polygonalization separately on the two objects, we might result in the case that the boundary between the two objects, they can sometimes have intersection, or they might be overlapping with each other. But if we do it in one go, then we can avoid this problem. Of course, this problem can be also avoided by, like, if we put more effort in the binarization, if we already can separate if we can already use maybe not GraphCut, but some other methods to do like instance recognition, and to have the semantic labels already very well, then this is possible to avoid that. But I think from how the method should develop, if we have a one-step method that already works, we should keep it instead of using two-step methods.
Okay, good enough for me. Then I had a few questions on the registration part. So you're saying you have 24 different possibilities for the directions, but in practice, very often you know which direction is the vertical. In LiDAR scanning, you always have the vertical, and even with image acquisition, usually images are oriented such that the Z direction projects to the top of the image. So you have some good hints on what is the vertical. So how much simpler is the problem if you know the vertical? And did you take this possibility into account in your code?
In my code, I did not take into account this possibility, since I on the data set I test, I did not have such information. But if we have already the vertical direction, this means that in the permutation of the three axes, we have one position that is already fixed. So we only need to permute the other two. So it's just two permutation with 4 possible orientation for each permutation, and also there is one orientation we need to do for the vertical direction. It might be well, for the vertical direction in the acquisition you described by LiDAR. Do we know for this vertical axis, we know the direction already, like what is pointing up or what is pointing down? Like if we know what is pointing up already, then we just have 8 candidate rotations in the end. So this would reduce our computation complexity a lot.
So will your algorithm be 3 or 6 times faster?
Oh well, it's not 3 or 6 times faster because for the 24 rotations we can already process them in parallel.
Okay.
If we have 24 cores, then we can do it all in one go.
Okay. Yeah, can you go to your energy term? I think it's slide 47. No, 45. Okay, it was that term. I'm not completely sure of what these distances mean. The sum is over planar regions or over points?
These are over the planar regions. So the distance field are approximated by the planar regions detected from the input point cloud. And for the surface mesh, we just take the triangles of the surface mesh.
Okay, and so you're summing, okay, one sum is over the planar regions and the other sum is over the points of the point cloud.
One sum is over one sum is like, well, the sum in here, in fact, the ND and NM are the point sampled, but the distance field is computed. Well, I would say it's approximated from the planar regions, and the sum is done on the point samples on the input mesh and on point sample from the point cloud.
Okay, because my question was, if you are in a case where your two different sets have only very partial overlaps, how is that taken into account in the energy? How do you take into account that the overlap is very partial and that many points do not have correspondences in the other scan? And let's say, is this energy robust to these very partial overlaps?
This energy, as I tested, it's not very robust to very low overlap. Like since we are penalizing as we can see from the energy, we don't weight any of the points. So we assume that everything should be present in the distance field. And so if we have a pair of inputs that only overlaps a very small part, this energy would actually ignore this fact and try to put these two geometric pairs like as close to each other as possible, since it's just defined on the distance. And we can actually try to extend this method by adding by weighting the, for example, by weighting the correspondences. If we have some prior information about how well the amount of overlap, or some prior information about some possible correspondences, and we can add weight to the sum to weight the contribution of each point sample. In that case, the energy would be able to take into account the low overlap fact. But for now, the algorithm I developed is not taking into this account.
Okay, and maybe one final question on the floor plans. Maybe if you can go slide 58. I think it was 58.
58? No, 58. The next page, I think. Sorry, the computer takes time to load.
So it seems like, for instance, in the bottom right image, that lots of rooms are completely closed and that you're missing the openings, the doors, and so it makes your rooms completely closed. Isn't there a structural problem in your method, because it's very hard to close the walls, because the extremities of the walls are very, very small segments and it's very easy to miss them? Wouldn't it be easier finally to just do a binarization of your image and then do something like a Douglas Plucker, where you would not have this problem of risking to miss the extremities of the walls?
Yeah, to so you mean so what you mean is like, for example, the case where the the third room, like the third room
all the
on
rooms
right.
on the all the rooms on the right part of the rightmost image seems to have been completely closed. And so in a 3D model, it's going to be problematic because you won't be able to access these rooms. They are going to be completely closed.
So this problem comes from as you described, as when we do the process of polygonal image segmentation within these very small polygons, we can sometimes miss the extremity of the very tip of the room because maybe in the input image the gradient is in fact not flat. Like it's like a rounded gradient at this very small scale. Then it's
and the edge is very, very small, so it's easy to miss.
The edge might be just be ignored. In that case, I agree that it would be better to incorporate some other detection method just to fix these problems. Like if we can add some rules that pay extra attention to the thin polygons, and or we can first to have a binarization of the floor plan. Like in this case, the binarization would work since it's more or less black and white, and we can add this additional image to help us if the polygon is like it overlays a region that has like that has wall and floor at the same time, these polygons should be further segmented. So if we can enforce the segmentation of these polygons to recover the door.
Okay, well, thank you very much. It's all for me. So I leave the other members of the jury, and I want to congratulate you again on this nice work.
Thank you, Bruno.
Thank you, Bruno. We now move to Nicolas Melado.
Thank you, and thank you for the presentation. It was very clear and well illustrated. So I didn't know that much your work, and with the presentation, I get a good balance between the concept, the other mathematical details and results. So that was really nice to follow this. So I have a few questions mostly on the second part, but I will start by the first. So I understand that you want to be able to process automatically layouts to generate your polygonal approximation to the construction. But I was wondering if we go in a context where we want users to be able to control a bit the way the polygonization is done. Is there a way to indicate where we want some edge to be located? Like in the example with this guy ending on the bike, if I want to have an edge between the grass and the concrete, how can I do that?
Okay, I get to a question I'll put up the slides or it's loading. Okay. In this case, in fact, how we should do the segmentation, like how many objects we should segment in the end, is indicated by the input semantic probability maps that we require. And this probability map we take from the learning-based methods. Like for example, here we use the Deep Lab v3. So it's here we do not have like the boundary between the concrete and the grass just because on this data set there's no label between them. They are all considered as background. So if we have a semantic segmentation method that can do the segmentation, that can distinguish these two objects, then we can just plug in our method to do the post-processing. Then we will have in the end a nice segmentation, polygonal segmentation that segment these two.
Also, so still different context. When I look at your formalism, seems that we could apply your approach on not on images, but on voxel grids, and to generate 3D meshes to segment voxel grids. Did you think about that, and what could be the difficulties if we go in that direction?
You mean taking the image segmentation to like voxel-based segmentation?
Yeah.
In that, I think it should, the basic formulation should be similar, since we can do the mapping, like we map all the line segments to planar shapes detected on the 3D, and we can also map the semantic probability map to like probability defined on the 3D voxel. So the whole pipeline should be able to be transferred to the 3D voxel-based representation. And the main difficulty and the reason that I did not think about this is that I have not found I have not seen like a 3D voxel-based segmentation methods that I can use their output to try my algorithm. And if that exists, and I think we can try our algorithm on those type of data. Some difficulty might exist because, for example, on the 2D image, like we can process easily large image like with 1 million pixels, and this high resolution image would help us to detect the line segments very well on the image. But on the voxel-based representation, even if we have like it's almost impossible to have 1,000 by 1,000 voxel, and in that case, we might end up with some very coarse voxel, like 100 by 100 by 100. Then detecting reliable plane segments on these very low resolution voxel representation might be very challenging. I haven't seen methods that do that well.
Okay, thanks. Okay, so now regarding the registration approach, and regarding the problem with the overlap. So yeah, it's like, as you said, in the perspective, the pipeline needs to be adapted to handle partially overlapping objects. And you mentioned in the discussion with Bruno the option to add weighting on between parts of the object to be able to. And I was wondering, when you start by registering your frames, in a way you maps one direction of one object to the other one, and could that be a good way to give a first guess of the mapping between the point cloud and the mesh, part of the point cloud and the mesh?
Yeah, so you mentioned so okay, so maybe this is not the slide. Okay, maybe we go to this more general slide. So yeah, the first step it is to map. Yeah, it is to have this planar shape representation and try to map the main directions to each other. And this step, for the low overlap case, sometimes this step is not a problem. Like we can still do the mapping of the directions, well. Like if we have a low, like if we have a case like we have a occluded building and with a building mesh, then the three main directions would more or less be the same if we have things partially occluded, like in the case of the building. Then in that case, this like this step would work, and we could align. We can do the rotate. We can still do the rotation alignment well with this low overlap input. And you mean that we can maybe get some intuition from like which part of the input could have correspondence in the other part?
Yeah, you know, when you align the frame, when you make a decision on which direction align on that direction, you know which plane contributed to that direction. So in a way, you're making a link between those planes.
Okay. I get what you mean. Yeah, in that, I guess that could be a way to get an idea about what planes have correspondences in the other input. If we have determined like if we can somehow determine the good alignment of the three frames without doing the refinement, if we have the like we know that this direction maps to the other to the other direction already, and we count the planes that contributes to this direction as being bound correspondences. In that case, I think we can add this information to the weighting of the later energy to say that the planes that are contributing to the recognized directions should be assigned higher weight, and the planes that does not align well should be assigned lower weight. We might be able to reweight the energy for the refinement step to get a better description of the low overlap case. So the question comes back to how we would know in advance how well the three frames should be aligned without doing the refinement first. For that, I indeed have no sort of a solution.
Okay. Thanks. Another question about the frames. So you generate the frame from a planar approximation of the point cloud, and so it seems to me that by changing the size of this plane from like local plane to aggregates, like what you show on this slide, in a way you like quantifying the direction, the main direction of the shape. And I was wondering if you try to play with that. So send, for instance, just unoriented normals and aggregate them and see if you get a similar descriptor that you could use. So that would avoid you to make the planar shape extraction at first.
And yeah, if we just input the oriented normals from the point, you mean that?
Yeah, or unoriented, you could ignore the orientation and make them contribute in the true direction, because then you work on the combinatorial of both direction. So
I'm not very clear about the question you asked. Do you mean by replacing like these? Do you mean by like ignoring the planar shape detection step from the point cloud by just taking the point cloud with like and count the points normal that contributes to the to a distribution of the normal?
Yeah, that's the other extreme, and there is a wall in between. There is a continuum between taking the point normals and the plane as you did. So just wanted to know if you play with that.
For that, for computing the three frames, I also tried before to use the point normals directly to get a distribution look like this, and it like they can be equivalent in some case and be not equivalent in some other cases. Like the case where it's equivalent is that when we have some sort of clean point cloud without too much noise and without and the point cloud they are uniformly sampled. Then the result from the extracted planar shape giving the distribution and the result from the point cloud giving the distribution would be very similar to each other. But if we have the point cloud that comes with noise and outliers, and if the point cloud is not uniformly sampled, like imagine if we have on the tip of the temple they are densely sampled, but on the base there is like almost nothing, then in that case the distribution would differ from the one that we use the planar shape detection, because for the planar shape detection step, what we hope to get benefit from is its robustness to noise and the outliers. And if we in those very extreme case, if we tune the parameter to make it to try to make it detect planes in the sparse regions, then it would potentially give a slightly better representation of the distribution.
Okay. And just to be sure, do you weight the directions by the area of the plane? Because you could also weight the direction of the point normal by the local density to account for variation of density.
In this slide here, the weight is assigned by the area of the plane, detected planes. But for the point cloud, it's in fact the reverse of the problem, because if we have a non-uniformly sampled point cloud and we weight so if we have a non-uniformly sampled point cloud, and if we weight by the inverse of the point density, then it can try to counter the effect and be able to give a representation that is more uniformly weighted. In that case it would be able to give a good distribution. That could also work. It's just that we think it's better to have like a sort of a unified representation that can be used to represent the point cloud, and the mesh and the planar shape is a good option to make everything more unified. And these planar shape extracted, they are not wasted. They are used again to approximate the distance field.
Yeah, I understand that. It's play the role as a regularizer of the data. That's interesting to have. Okay, on slide 49, you mentioned the fact that you try to apply noise, and you show some robustness to noise. But the thing is, you use a Gaussian noise, which is isotropic, and might not affect that much the main direction. And I was wondering if you try to add like directional noise, like if when you got LiDAR data, you got more noise in one direction, specific direction than the other one, then that could affect the orientation, and so I guess penalize more your approach. So did you try that?
For that, unfortunately, in the thesis, I have not tried on the LiDAR data that has this property. Though I guess in that case, if we have like a directional noise that favors some directions, that would affect this step of detecting the three frames. Like if we have a favorable direction in the LiDAR acquisition, then that direction might take the position of one of the main directions already in the three frame, and we are only left with two remaining directions to detect from the point cloud. And in that, but I cannot comment much since I have not had a look on that types of noise in the LiDAR data.
Okay. Okay, I have one last question. So in this work, you represent your point cloud by 3 non-orthogonal directions. So that gives you a frame. And when you discuss with Bruno, you mentioned the fact that, let's say, if we know the vertical direction, we could go back to 2 directions. And I was wondering, as the direction are non-orthogonal, you could go for more than 3. Could be 4 or 5.
Mm-hmm.
And so I'm wondering if you look at this, and how do you justify the fact that you have only 3 of them?
Okay. Yeah, indeed, we can have more directions if we want. It's just that since we are putting like a focus on the urban objects, and typically they are well described by 3 directions, which is already enough. But if we have more complex shapes, and it is an option to add more directions that we like just increase the number of clusters in the EM algorithm, we can have more detected shapes. We can have more detected axes for different types of shapes. And in my thesis, I have noted down the experiment to justify, like, for what type of objects, how many number of axes we should assign to each type. I believe that's an interesting direction to work on, if we can find the link between the optimal number of directions and the shape characteristics.
Okay, interesting. So that's all for me. Thank you again for the invitation and for the presentation and the discussion. That was very interesting. Thank you.
Thank you, Nicolas. Maybe Florent, you can say a word.
Okay, thank you. So I will try to be quick. So first, I would like to say to I appreciated working with her. So she's a very pleasant person to work with, rigorous and hardworking. So it was really a pleasure from my side. I would like to point 2 things regarding our PhD. So for our first project on the polygonalization of images, the method she proposed look a bit simple and natural when we look at the slide, but many things have been tried before arriving to this result. And even if it looks obvious like that, it was not obvious. It took a bit more than 1 year to get to this formulation, and many other things have been tried. The second thing I would like to say is that Mu did a break, a 6-month break during a PhD around the second year, I think. And so she did a 6-month internship in China at Alibaba. And during this internship, there was a COVID crisis, and she could not come back to France. And after, with visa issue, it was too much complicated. So she had to finish her PhD in China alone, in difficult working conditions, and she could not benefit from the physical presence in Riyadh. So I wanted to point that to the jury. So now maybe just one question, a quick question. When we look at the conclusion of the 2 methods you proposed, especially the one for the polygonalization of images, it looks like that the conclusion could be that traditional computer vision with traditional geometric processing tools can still compete well with recent deep learning methods, especially when the methods that try to extract, deep learning methods that try to extract geometric structure, like polygons in images or like compact polygon data. My question is, do you think that this will still be the case in 5 or 10 years? Or do you think that for extracting such geometric structures, the deep learning method has some problem of scalability or quality because they mainly train on synthetic data that they won't be able to deal with? Do you think that traditional method is failed to disappear, or do you think it will still survive on this type of problem?
Regarding this question, from what I have learned throughout the course of the PhD is that type of method, they have their own strengths and drawbacks. I believe that deep learning method for the current stage, maybe in the near future, is still more adapted to like structure, like data with very well grid structure, like images or 3D volumes, because most of the effort has been put in this representation, and the network frameworks, they are very well adapted to this representation. But when it comes to geometric, like geometric representation, like if we want polygons from images, or if we want to construct a mesh from point cloud input, for the deep learning methods, it could possibly be that there have not been too many efforts put in this direction. People haven't tried everything possible, or they haven't tried all better formulations for the problem to make this work. And it also could be possible that there might not be a very good representation in the end, even if we have exhausted all the ways to formulate it in a differentiable manner. And the strength of the traditional geometric approach, the geometric processing algorithms, is that, well, they can do discrete optimization very easily, and they are numerous algorithms that help us to do discrete optimization, and there are numerous geometric operations that we can do on the mesh and on the point cloud. We can do a lot of stuff. And so if the deep learning methods can surpass the geometric methods, it means that there would exist a differentiable operation, some differentiable loss that can be applied to geometric data, and will be, in that case, then it can outperform the current traditional methods. But I believe it's still quite far from what we look for. Just a side note, it's what I discovered in comparing deep learning methods for the registration problem. For example, we have for the deep learning method, on the registration problem, I compared to two deep learning methods. One is DCP, that is trying to force a transformer architecture on the point clouds and do the correspondence from there. And the other is DGR, that use a volumetric representation. Like the volumetric representation works very well because the deep learning method is very well designed. Like the convolution operation can be very well adapted to do the optimization. But if we want to process very point cloud without much structure, then it has difficulty to actually produce some sensible results. Well, it works on the original DCP paper because they use very clean input data. So there is a risk of generalization when it comes to real world data. Now, it's just a side note.
Okay, thank you.
Okay, thank you, Florent. I'm going also to ask a few questions. Actually, I have plenty, but I try to refrain. Thank you very much, Mu, for this nice presentation, and also for the manuscript, which is very pleasant to read. Regarding the chapter on polygonization, can you tell us a bit more about the sensitivity to the line segment detector that you've been using? So we've been already talking about the sensitivity to the initialization, but within the kinetic framework, which gives the best results, there's still possible sensitivity to the line segment detection. So what's your experience with that?
So for the line segment detection, this is a part that I did not talk much in the presentation. Well, there are several ways to do the line segment detection. Like for example, the kinetic method, they use LSD as a line segment detector. That is based on statistical analysis on the image gradients and do the extraction of line segment based on the statistics. And there are also like some deep learning methods that can do the line segment detection nowadays, for which that I have not tried. And for our process, in fact, we use an even simpler line detection method. We just use the region growing on each of the small polygons to further detect the line segments that in each of the polygons. And this is because we are taking into account like the processing speed. If we use very complicated methods in this iterative framework, even though that we can detect maybe perfect line segments on each of the polygons, it will take a lot of time for it to finally converge. And if we have already like a very perfect line segment detector detecting every possible line segment that is suitable for the segmentation, then why don't we use the kinetic partition or other partition method and do graph cut already? Here what we see is that for now, at least so far, no line segment detector is like there exists no perfect line segment detector. Like all the methods have some sort of drawbacks, and we have to live with that. So in this work, we try to do this part of the dirty work to do refinement on the initialization that is not perfect, and to also live with non-perfect line segment detector by allowing, like, we just use region growing, but we allow more line segments to be detected, like even if most of them are wrong. And we do the segmentation of each polygon into smaller polygon and try to look for a good configuration in these in this large amount of polygons. So this is more of a practical, so this algorithm is more or less in the end a practical choice that we take into all these factors and finally converge to this option.
Okay. Yeah, I understand the limitations somehow. Regarding the registration part, so you have some sensitivity to the degree of overlap between the 2-point clouds or between the point cloud and the mesh. And so I was wondering whether you thought about ways to be less sensitive to that, in order to apply your method to cases where you possibly have a smaller overlap between the two shapes.
Yeah. Yes, so the overlap is indeed a problem that we encounter in both the registration project and also in the pipeline that we try to apply the polygonalization and the registration into the application. So I guess we have, in order to counter this, the effect of low overlap, we really require some methods that tell us the correspondences between the between the input point cloud and the mesh, to know like which part we should focus more, since they have correspondence, they should be aligned well, and which part we do not care, since they are unlikely to exist on the other pair. So from what I discussed with Nicola before, so maybe assigning weights to the planet shapes based on how well they align with how well the three frames they contribute in the end align well with the other three frame might be a way to do this, but it could also be problematic for perhaps this example. Like in this example, if we detect the three frames, it's more or less like the XYZ axis, like orthogonal to each other, and the planet shapes would be all very well counted because they are on these three directions, and they are well, if they are well aligned, every planet shape would contribute to one of the three direction. So in the end, maybe we still need to either modify to adapt some methods that considers like correspondences between the pair to our method. Like we do not need point-to-point correspondences here. In order for the method to work with low overlap, we only need correspondences on the scale, like on a large, like on the high level. Like we only need to know like which part is less likely to appear in the other, but not like this point should be correspond to the other point. So I think there is a small difference between the current correspondence-based method that gives point-to-point correspondences and what we want in the end. Like what we want is not point-to-point correspondences for the method to work.
I was thinking of a method which is called point cloud registration method, which is called Predator, which is a run-stack-based, deep learning-based method, which tries to compute features on points and to see how much they look alike. So there's a kind of confidence on whether a point is likely to match another point. And they use that as an information for the run-stack exploration. And I was thinking that maybe it could be so using maybe a different precision recall trade-off. It could be a kind of pre-processing stage that you could use in order to filter out points that are less likely to have correspondences in the other shape. And that could be a way to somehow clean the original point cloud. And then you could apply directly your method, possibly also with additional weights. But do you think it would make sense to do this kind of thing?
Yeah, I think it would make sense if the method you mentioned can produce a sort of probability associated with each point, like the probability measures how likely it has correspondences with some other points. Then that would give us a good idea of how we should, like as you mentioned, how we can clean the input beforehand, and just to give just give the cleaned input to our method and do it to apply it directly, or we can use their like computed probability to weight our energy function, and maybe like it might also be possible that we can connect to these two methods and do the update like alternatively. Like if we can first apply their method, get the probability, then we do our alignment based on their probability and give some alignment. Hopefully it's better than Ransack, and then we give back their method this new alignment and ask them to compute the correspondence probabilities, maybe giving a better estimation, and then we do the update. So that would be a way to proceed.
There will still be a restriction regarding a method like Predator, in the sense that it assumes that the scales of the 2-point cloud is the same, and your method is much more general because you don't know the scale in advance. And regarding that issue, I was thinking, so for images, you have scale invariant features, like even like deep learning methods like SIFT. It's even in the name of the method, scale invariant. And so I was wondering, so if you were using scale invariant 3D features, that is features that you could compute on a point cloud, but that would be scale invariant, maybe that could be also a way to address that correspondence as a pre-processing stage that you could use. What do you think of something like that?
Yeah, yes. Although I have not personally looked into scale invariant 3D features, but from the success of SIFT, I guess if we have a 3D feature that is that can be scale invariant, and if it's reliable enough for this type of data, then it would be a nice way to add to the component of like Predator to give us correspondences that exist between like two inputs of different scales. And it's a very interesting direction to look at.
Now moving to the last part of your thesis. So there was also some part of the discussion regarding that, I think, and it's even in the perspective that you've presented. So how hard do you think it would be to learn once and for all, in some sense, or on a given data set, enough semantics to be able to recognize, let's say, walls in a floor plan, like to be able to classify an edge as being an edge, a wall edge, or this kind of thing? Do you think it would be possible to do that, so that there would not be any human intervention to bootstrap your method?
For the deep learning methods, to get like good like a good semantic maps on like diverse type of floor plans, I think it's still a very challenging problem. It's like we can see 1 or 2 papers on this topic every year, and it's still, and for many of like first of all, for many of these types of works, they still work on very clean floor plan images, like clean in the sense that it's raster floor plan images, or floor plan images that we can find by like typing in Google floor plan images, those type of clean data. Then the training could work well on first, it has been shown that the training works well on this type of data. And as long as we have enough labels and enough training set, the current pipeline should be able to do the pixel segment, like the pixel-wise segmentation well. The other point is that as a floor plan image, it's usually very diverse. Like from the floor plan images that I see nowadays from every building from online, they are not drawn according to the same style, and they might be very different from each other. Like for the grayscale floor plan I show here, the white is the floor, and the white is the floor or the background, and the black is the wall. And from some buildings, for example, the building of Alibaba that I saw the other day, it's inverted. The white is the wall and the black is the background. So if our training has not taken this like drastic change into account, then it might not be able to generalize very well. But well, there could also be some. There also could be some way to do so. Like maybe the train network would focus not on the color cues, but also more on the structures. Like maybe what they see is like more or less the gradient of the image. Then it doesn't matter whether the color is inverted or not. It's just that we need in order for the method to work like without a human intervention at all, it really requires a lot of training examples, like to take into account the different styles.
Yeah, and so regarding this, the large amount of variation in floor plans, there's also that other thing, which is that they are very abstract, and that they might not be a faithful representation of the actual dimensions of the buildings. Very often they are not drawn by architects sometimes. So when you imagine you have a very nice point cloud, whether it's LiDAR or MVS or whatever, but with proper relative dimensions, and then you have this floor plan, which doesn't respect the actual dimension, and a room might be larger, another room smaller. So what would be the impact of using your method with an incorrect floor map, incorrect in the sense that the sizes of the rooms are not correct?
I guess in that case, it's very difficult for the method to work just because first of all what we estimate from the floor plan, like the model to the point cloud is an isotropic scale. Well, we just compute one scale that enlarge or shrink the model to fit the point cloud. But in the case you described, is that every building, they might be different from their original ratio, and like the rooms, maybe the aspect ratio of one room is different from the aspect ratio of another room. So there exists no uniform scale, like even in the 2D space to correct this floor plan. So I guess to make that work would be like we might have to go to like non-rigid, like those non-rigid registration in the end.
Yeah. Yeah, actually, even there's a difference between what the architects draws, whether it's in Revit, Archicad, or I mean any of the applications that the architects use to design a building, and what people actually construct. Our experience with at École des Ponts with Bouygues Construction, which is a large construction company in France, but also internationally, is that there's a discrepancy between what people actually build and the architectural plan. Not even talking about the floor plans or the safety evacuation plan, which are even more abstract. Just a last thing, I was curious about. So you talk about Matterport. So I don't know whether what we see here is a Matterport scene, but I was wondering. So does Matterport 3D offer floor plans, or what did you use as the overview?
So for the Matterport dataset, in fact, what I do is that I draw the floor plans by myself, by hand.
Okay, I understand, because I had never seen floor plans for Matterport.
So if you need floor plans of Matterport, I can send what I have to you.
Okay, great. Well, oh yes, just one question. So, is your code available? So I know that for the polygonization it's available, but is your code available also for the registration, or do you plan to make it available?
Yeah, I plan to make it available because the paper is currently still under review at the conference. Once it's once we know the result, I will prepare the code to be released.
Okay, great. Okay. Well, thank you very much for your answers. So maybe we can move now to a more private discussion. So I don't know, Florent, how you want to organize that.
So first, Mu, can you give me back the end on the?
Okay, so Florent, can you tell me how can I? Okay, I give you back.
Okay, so Mu and Mulin is broadcasting the defense on YouTube. I will send you a Skype message when you can come back.
Okay, yeah.
Gaëtan, I don't know why you're here, but you should not be here. So please disconnect and go on the YouTube channel.
Okay, I'll disconnect now and see you later.